So let me switch to here. All right. So like I said, I'm going to post a more professional video of this. And I'll have different figures. So I'm not like with this one, like this is all one figure and I'm gonna have to like scratch out part of this. So it's gonna look a little messy during the live stream. But in the video that I'm actually gonna be recording, it's gonna look a lot cleaner. So here's the situation. I have a box that's at the top of a ramp and it's going to slide down the ramp and it's going to travel down this way. And then once it hits the bottom of the ramp, so from this point all the way until it hits the spring, this is going to be traveling horizontally and there's going to be no friction. Okay. And while it's traveling that way, so I'm going to kind of break this up into, so this would be state 1. And then once it gets down to the bottom part, this would be state 2. And then I have like what I was working on when you guys just first started the meeting. I was working on the third state where I had this spring kind of, I changed the opacity on it. So it showed like where it was previously. And then the one that was like full, like there was no opacity, like it was fully visible. It was kind of located like right here. And then you saw the spring obviously compressed. And then this would be the delta X. And this would be the point where it would be state 3. Okay. So I think the best plan of action is in this live stream is to discuss what's actually going on and what energies are present at each state. So what I'm going to do is review the questions that you ask yourself for each of the states. So there's 3 questions, and at each of the states, after you've asked these questions, this will dictate what energy is present at each of those states. So the very first question, is there a height from the ground? And when I make the video, this will be typed up and it'll be perfect. So is there a height from the ground at state 1? So remember, state 1 is going to be right here. And this question is referring to U gravity, or the gravitational potential. Now, it doesn't matter what order these are in, but as long as you ask all 3 of the questions, it'll walk you through it. So is there a height from the ground at state 1? So remember, state 1, we're just focused right here. Is there a height from the ground? So this line right here, this is the ground here. And obviously there is a distance from the center of mass down to the ground. So since there is a height, gravitational potential is present. Now at state 1, this is the instant right before I release the box, or right after I release it. So it hasn't had any time to change its position over time. So that means that there's no velocity. So the second question is, is there a velocity? And this one obviously is pertaining to kinetic energy. Anytime I'm talking about something moving, that's going to talk about kinetic energy. So this is the instant right after I release it, so it hasn't had enough time to start moving. So there is no kinetic energy present at state 1. The third question is, is there a spring that's being compressed or stretched? This is obviously U elastic. And at this point, the mass is over here. So the spring's over there, so it's not compressing the spring. So there's no U elastic at state 1. So the only one that we got a check mark with, check mark for, is going to be gravitational potential. So at state 1, we have gravitational potential. Does anybody want to chime in and make a guess of what it would be at state 2? Oh no, my drink's downstairs. Anybody? So once it's reached the bottom of the ramp, is there a height from the ground? Nope, it's traveling across the ground. Is there a velocity? So when something is slid down a ramp, obviously it's moving once it hits the bottom, and we're assuming no friction. So yes, there is a velocity. And at this point, the spring is not being compressed or stretched. So there's no U elastic. Try to keep the colors the same. So at state 2, this is going to be kinetic. And then lastly, this is going to be where the box has compressed the spring. And the box is right here. So the box has compressed the spring. And we go through the same 3 questions. Is there a height from the ground? No, it has not gone up or down. So there's no height from the ground. Now this is the part where people get confused. Is there a velocity at the point where it's been it's reached its full compression and it's getting ready to launch the other way? The answer is no. There is no velocity, because in order to reach its maximum compression, it's no longer traveling in that direction. It has now been switched and it's getting ready to launch the opposite direction. So anytime that you're traveling, you're switching signs for it. If I'm going forward and then I go backwards, at some point, it's called the point of inflection. It's where it crosses the horizontal axis. If you're plotting it, it's when it reaches 0 and it then becomes positive or negative, respectively. So at the point where it compresses fully and then gets ready to launch back, the velocity must be 0 at that point. So there's no kinetic at state 3. And then obviously U elastic is present. Okay. Is there any confusion so far? Okay. Now, remember when we first started talking about energy, I said that energy can't be created nor destroyed. Energy is conserved. So the total amount of energy in this whole scenario remains constant. There's no friction. There's no air resistance. So nothing is lost to the environment. All the energy is conserved. So all of my energy at state 1 must equal, like if I got a numerical value, say 500 joules. If I had 500 joules at state 1, I must have 500 joules at state 2. And I also must have 500 joules at state 3. Is there any confusion about that? So state 1 is 500 joules, state 2 is 500 joules, state 3 is 500 joules. So if they're all the same number, that means that we'll do this. Energy total at state 1 equals energy total at state 2 equals energy total at state 3. All the energy is conserved. So that means that all the energy that I start with will be at state 2 and will also be at state 3. No energy is lost. Hopefully everybody's tracking with that. Now, this is where we use these. So the only type of energy at state 1 is U-grav. So gravitational potential energy at state 1 is equal to the kinetic energy at state 2, which is also equal to the elastic energy at state 3. Now, it's important to notate at which state it is, because the kinetic energy at state 1, so E total, like just as a reminder, I'll put this over here. So this is what E total equals. So it's U-grav plus kinetic plus U elastic for each state. And hopefully you guys can recognize that if I did this for each of the states, I would have all three of these for here, and for here. And that would get really, really messy really quick. So that's why I developed this method to help you kind of cancel out which ones are present for each state. So you don't have to write things that you don't need. Cool. So that's why I've notated with a subscript. This is gravitational potential at state 1, kinetic at state 2, U elastic at state 3. Okay. Now, depending on the questions that I ask you, there are some variables that I will give, and you will have to use that information to solve for something that is unknown. So in particular, we'll say I'll give you the mass and I will give you the spring constant. Let's see, will that work? Yeah. All right. So the only knowns that I'm going to give you in this problem. Now, in this particular example that I'm doing right now, that's what I'm going to do. So I'm going to give you what did I say? Mass. And then I'm not going to actually give numbers right now. I just want to get the basics down. Gravitational potential, or acceleration due to gravity, and then the spring constant K. So these are my only knowns. And I'm going to ask you to find the velocity at state 2. And then I'm also going to ask you, what is the amount of the spring, how much did the spring compress at state 3? Oh, and I guess I need to give you the height. Now, these are the variables that I can give you. So I will give you 4 of them, and you will have to solve for 2 of them. This would be height 1. Now, because this is an honors class, I may switch it up depending on how time is. I may not. It'll all depend. But I will provide an example so you can go back and review it in the event I do decide to give you a different version of it. Hopefully this is making sense. Okay. So what we can do is, if I'm trying to solve for V2, where is V2? Remember, the subscripts represent what state it's in. So V2 is obviously going to be in state 2. Okay. So what I'm going to do is I'm going to substitute in what the formulas are for ugrav and kinetic. So ugrav is just mass times gravity, and because it's at state 1, this is going to be H1. That's going to be equal to my kinetic energy, which is 1/2. Whoops. Times the mass times the velocity squared. Now we're only worried about V2. And when you're writing this down, make sure that you put the subscript like that. Give myself a little bit more space. Okay. So my objective is I want to solve for V2. Cool. So if I want to solve for V2, I need to get everything else over to the other side. And this should look familiar because I did a problem like this before. Since I have a 1/2 here, in order to cancel that out and make it a 1, I multiply both sides by 2. And then I divide both sides by m to get rid of the m. So it gets rid of the m's here. That cancels. M's cancel. And then below here, I've got 2 times mass times gravity times h1 equals V2 squared. And in order to get rid of the square, I square root both sides. So the square root and the square cancel out. And the equation that I get for V2 is going to be the square root of 2 times the, or no, mass. Apologize about that. The mass is canceled here. 2 times gravity times h1. Apologize about that. That's all in the square root. So that would be the equation for V2. So since I've already gone through this example, you don't need to do any of this algebra. Like any of the stuff that I just did right here, you don't need to do that on the assessment. All you need to focus on is if I ask for V2 and I give you these knowns, you can just plug in those knowns into this equation and you already have V2. Cool. All right. Now, because I have not given you values, let's do the same thing, but solve for how much the spring has been compressed. Now, since I don't have any values, we're going to have to figure out some way to solve for something that's in here. And let me actually copy this down. Copy this down here. Okay. So my delta x at state 3 is obviously in state 3. Cool. Am I going to give you the equations? Yeah, of course. So that's why I started this. So I haven't decided whether or not I'm going to give you this particular equation or if I'm just going to give you the basic equations. And just as a reference, I'm going to put these up here again. All right. So I'm debating on whether or not to give you those three equations. And then you guys, if you haven't written down the already solved one, you should be able to figure out how to do it. That's kind of emphasizing that you should write this down, like the start equations. But in the event that you haven't written those down, yes, I can. I will provide these to kind of incentivize you guys to, show up on time to class and make sure that you're paying attention to the lectures. Cool. Do I need to make this bigger? Okay. All right. So in the event that I'm solving for delta x at state 3, I know delta x is right here. Now, I do not have the variables to get a value for kinetic energy. Okay. So remember, kinetic energy is 1/2 mv squared, right? I'm given the mass, but I am not given the velocity. Now, you might be thinking to yourself, well, Mr. Applewhite, we just solved for the velocity. When we do this, we're going to have to round. So that's not going to be an accurate answer for v sub 2. Okay, we're going to have to round, so it's going to be an approximate answer. The better way to do this, the most accurate way to do this, is to only utilize things that we absolutely know. So I have all of the variables for my gravitational potential. Mass times gravity times height 1. Mass times gravity times height 1. So in that sense, I have the most exact for gravitational, and then I can use that to solve for whatever I don't know in here. Does that make sense? Because all three of these are equal, I can set these two equal to each other, I can set these two equal to each other, I can set these two equal to each other, and we can solve whatever. Does that make sense? Hopefully going back and watching this, it might click. I know it's really early to be doing all this algebra. So what we're going to do is we're just going to focus on this. So U-grav and U-elastic. So this is at state 1, this is at state 3. So when I expand these, I get mass times gravity times h1. And that's equal to 1/2 times the spring constant times the change in x for state 3, and that's squared. And I'm solving for delta x3, so delta x at state 3. So I do the same thing as I did before, multiply by 2 to cancel out the 1/2. Do that over here, divide by the spring constant, So after that, I have 2 times the mass, like nothing cancels out over on the left side. So 2 times the mass times gravity times the height at state 1 over the spring constant equals my change in x at state 3 squared. Now, in order to get rid of the square, just like before, I square root. So the equation for that, if I'm asking you to solve for how much the spring is compressed, it's going to be 2 times the mass, acceleration due to gravity, times h1, divided by the spring constant, all under the square root. Now, this equation might cause some issues for some people if you're using your iPhone or some sort of non-graph or wouldn't necessarily non-scientific calculator. When you start plugging the numbers in to this part right here, this numerator, well, I guess it wouldn't necessarily matter if you had multiple. Never mind. Forget that I said that. When you are plugging values in, I would highly recommend using Desmos, because with Desmos, it will make sure that this radical is applied to the entire fraction instead of just the numerator. I don't know why or where the disconnect is, but I have some students in the past that think that this is the same thing as that. And obviously it's not. The radical in this case is applied to the numerator and the denominator, but in this situation, it's only being applied to the numerator. So make sure when you're writing this down, you take note and make sure that the radical goes all the way down. Okay. Now, since I haven't really seen y'all's work, like handwritten work this year, I don't know if that's really applicable to you guys. But yeah. Okay. And this is pretty much what the assessment's going to look like. So I'm going to ask you to solve for 2 different things. I'm going to just do a brief overview. So the situation is I have a mass, and it's going to be sliding down this ramp. It's going to be traveling horizontally without friction or air resistance. It's going to be compressing the spring, and then the instant right before it gets launched back, this is going to be state 3. State 2 is when it starts traveling horizontally, and state 1 is when it's at the top. I will give you 4 pieces of information, and it can be any order of these, but I will give you 4 pieces of information and ask you to solve for 2 of them. I could run this in reverse. I could tell you how much it's been compressed. I can tell you the mass, I can tell you the gravity, and I can tell you the spring constant. And then I could ask you, what is the velocity at state 2? And then also, how high up the ramp does it go? So then we would just be switching these 2 variables. Does that make sense? Okay. So the way we go through, we have to figure out what type of energy is at each state. So I asked these 3 questions for each of the states. So at state 1, is there a height from the ground? Is there a velocity? Is there a spring that's being compressed or stretched? And this is telling us, like, answering these questions helps us fill out this part. It tells us what energies are at each state. And that helps us clean up this part. So the energy at state 1 is equal to the energy at state 2, which is also equal to the energy at state 3. So E total 1 equals E total 3, and so on. So the only energy that's present at state 1 is gravitational. State 2, it's kinetic. State 3, it's elastic. Instead of having to write all of this for each one of the states, answering these questions and figuring out which energies are present, which energies are present, it helps us cancel out particular energies. So this is our overall conservation of energy equation. And then depending on which variable you're solving for at that time, I plug in the values or I plug in the formulas. So in this case, we were solving for V2. I did the algebra. And if you're paying attention to this lecture and you write down this equation in your notes, you don't need to do the algebra. I've already done it for you. So if you can recognize that if one of my states, or the state that I have all the information for, is the gravitational state, and I'm asked to find the velocity in the secondary state, this is the equation that I need. And I do the same process with state 3. Since I'm given everything for the gravitational energy state, I can use that here. And then I can use that information to solve for the elastic energy. And you don't have to do the algebra. I've already done it here. And that's when you would use this. Cool. And what I'm going to do is when I do the, is it always going to be V2 or is there a V3? So the V2, V3, H1, these subscripts indicate what state it is. Okay. So it's actually good that you brought that up, because when I do this in a more professional way, like when I make the actual video, what I'm going to do is I'm going to make state 1 be down here. So the box is getting ready to be released. So this would be state 1. State 2 would be traveling right here, right before it goes up the ramp. And then state 3 would be when it reaches the top. Does that make sense? So it doesn't matter what order they're in. The subscripts just indicate what state you're referring to. Because technically each of these states has all 3 of these energies. So this could be a ugrav 1, kinetic 1, elastic 1, ugrav 2, kinetic 2, elastic 2, and same thing with state 3. The difference is for kinetic 1, this is just 0 because there's no velocity. So when I'm answering these questions, is there a velocity at state 1? No. That's going ahead and marking this out, making it 0. Does that make sense? So the equation is always going to be the same regardless of the state. These equations, these formulas for these, yes. The only difference is like depending on which state. So if we're talking about state 1, mass doesn't change, gravity doesn't change, so it would be H1. Mass doesn't change, so V1, and then K, the spring constant doesn't change, so it would be X1, delta X1. But if we're talking about state 2, this would be H2, this would be V2, this would be delta X2. And if we're talking about state 3, you can probably guess, it'd be H3, V3, delta X3. Does that make sense? Is that more confusing, or did I clear it up? Yeah, so this is I kind of condensed everything in a single lesson. But once, like when I go over this again, hopefully it'll click. Like it'll have some time to marinate. So what we can do tomorrow is like I'll actually have the figures down and completed. And instead of going from up here down this way, what we're going to do is we're going to reverse it, and we're going to start down here and then launch it up this way. So then this would be state 1, state 2, state 3. but it's the same process. The conservation of energy remains the same. And if I had the same values, then I would get the same numbers, regardless of whether I started over here or if I started over here. Does that make sense? No energy is lost, so I should get the same values no matter where I start. Make sense? And if it doesn't, it's fine. It's not like the fact that you don't understand it right now, that's perfectly fine. Um, this right here is all right. There's Chris. The stuff right here, this is what the assessment is going to be on. So after you've had practice, this is what you should be able to do. No problem. Okay, so this is kind of some insight of what to expect. I'm not expecting you guys to fully comprehend this right now. I want you guys to understand, like, this is where we're going, and we're going to have some more practice with just between two different states, or figuring out which equation to use. Okay, so don't worry about that. If you're apprehensive about that, I will take care of that. Okay, I'll make sure you have all the tools you need. Cool. That's right. You better believe me. Alrighty. So I'm going to go ahead and